The vanadium redox battery is a type of rechargeable flow battery that employs vanadium ions in different oxidation states to store chemical potential energy. The vanadium redox battery exploits the ability of vanadium to exist in solution in 4 different oxidation states, and uses this property to make a battery that has just one electroactive element instead of 2. For several reasons, including their relatively bulky size, most vanadium batteries are currently used for grid energy storage, such as being attached to power plants or electrical grids. Building on earlier research on flow batteries, the possibility of creating a vanadium battery was explored variously by Pissort, NASA researchers, and Pellegrini and Spazienta. The first successful demonstration of the all-vanadium redox flow battery employing vanadium in a solution of sulfuric acid in each half was by Maria SKYLLAS-KAZACOS and co-workers at the University of New South Wales in the 1980s. Their design used sulfuric acid electrolytes, and was patented by the University of New South Wales in Australia in 1986. Organizations involved in funding and developing vanadium redox batteries include Energy Technologies and Ashlawn Energy in the United States, Renewable Energy Dynamics Technology in Ireland, Gildemeister AG in Germany, Selenium in Thailand, Ronca Power and Prudent Energy in China, Sumitomo in Japan and H2, Inc. in South Korea. The main advantages of the vanadium redox battery are that it can offer almost unlimited capacity simply by using larger storage tanks. It can be left completely discharged for long periods with no ill effects. It can be recharged simply by replacing the electrolyte if no power source is available to charge it. And if the electrolytes are accidentally mixed, the battery suffers no permanent damage. The main disadvantages with vanadium redox technology are relatively poor energy-to-volume ratio. Although recent research at the Pacific Northwest National Laboratory has doubled energy density and the system complexity in comparison with standard storage batteries. Operation. A vanadium redox battery consists of an assembly of power cells in which the 2 electrolytes are separated by a proton exchange membrane. Both electrolytes are vanadium-based. The electrolyte in the positive half cells contains VO2+ and VO2+ ions. The electrolyte in the negative half cells, V3+ and V2+ ions. The electrolytes may be prepared by any of several processes, including electrolytically dissolving vanadium pentoxide in sulfuric acid. The solution remains strongly acidic in use. In vanadium flow batteries, both half cells are additionally connected to storage tanks and pumps so that very large volumes of the electrolytes can be circulated through the cell. This circulation of liquid electrolytes is somewhat cumbersome and does restrict the use of vanadium flow batteries in mobile applications, effectively confining them to large fixed installations. When the vanadium battery is charged, the VO2+ ions in the positive half cell are converted to VO2+ ions when electrons are removed from the positive terminal of the battery. Similarly, in the negative half cell, electrons are introduced converting the V3+ ions into V2+. During discharge, this process is reversed and results in a typical open circuit voltage of 1.41 V at 25 degrees Celsius. Other useful properties of vanadium flow batteries are their very fast response to changing loads and their extremely large overload capacities. Studies by the University of New South Wales have shown that they can achieve a response time of under half a millisecond for a 100% load change, and allowed overloads of as much as 400% for 10 seconds. The response time is mostly limited by the electrical equipment. Sulfuric acid-based vanadium batteries only work between about 10 to 40 degrees Celsius. Below that temperature range, the ion-infused sulfuric acid crystallizes. Round-trip efficiency in practical applications is around 65 to 75%. Proposed improvements: second-generation vanadium redox batteries may approximately double the energy density and increase the temperature range in which the battery can operate. Despite the traditional pumping requirements, one company, name of company needed, has focused on electric vehicle applications, using rapid replacement of electrolyte to refuel the battery. Energy density. Current production vanadium redox batteries achieve an energy density of about 25 watt-hours per kilogram of electrolyte. More recent research at UNSW indicates that the use of precipitation inhibitors can increase the density to about 35 watt-hours per kilogram, with even higher densities made possible by controlling the electrolyte temperature. This energy density is quite low as compared to other rechargeable battery types, and lithium-ion 80 to 200 watt-hours per kilogram. Researchers at the Fraunhofer Institute for Chemical Technology claim to have built a prototype for an improved cell, stating, "We can now increase the mileage 4 or 5-fold to approximately that of lithium-ion batteries." This same article makes a very optimistic claim that vanadium flow batteries can be recharged at a gas station by simply filling the vehicle tanks with fresh electrolytes. Applications. The extremely large capacities possible from vanadium redox batteries make them well suited to use in large power storage applications, such as helping to average out the production of highly variable generation sources such as wind or solar power, helping generators cope with large surges in demand, or leveling out supply demand at a transmission-constrained region. The limited self-discharge characteristics of vanadium redox batteries make them useful in applications where the batteries must be stored for long periods of time with little maintenance while maintaining a ready state. This has led to their adoption in some military electronics, such as the sensor components of the Gator mine system. Their extremely rapid response times also make them superbly well suited to UPS-type applications, where they can be used to replace lead-acid batteries and even diesel generators. Also, the fast response time makes them well suited for frequency regulation. Economically, neither the UPS or frequency regulation applications of the battery are currently sustainable alone, but rather the battery is able to layer these applications with other users to capitalize on various sources of revenue. Also, these capabilities make vanadium redox batteries an effective, all-in-one solution for microgrids that depend on reliable operations, frequency regulation, and have a need for load shifting installations. There are several notable currently installed vanadium batteries: a 1.5 MW UPS system in a semiconductor fabrication plant in Japan, a 600 kW 6-hour system installed by Prudent Energy in Oxnard, California, USA, a 275 kW output balancer in use on a wind power project in the Tomari Wind Hills of Hokkaido, a 200 kW 800 kWh output leveler in use at the Huxley Hill Wind Farm on King Island, Tasmania, a 250 kW 2 MWh load lever in use at Castle Valley, Utah. 25 kW units installed in St. Petersburg, Florida, under the auspices of USF's Power Center for Utility Explorations. A 100 kWh unit supplied with 18 kW stacks manufactured by Cellstrom has been installed in Vieiraca as part of an integrated energy concept called Photon Pharma. A 400 kW 500 kWh output balancer in use on a solar power project in a Bilasange village in Sumber Island, Indonesia. A 50 kW 100 kWh peak shaving for manufacturing facility in Gongju, South Korea. a 5 kilowatts, 60 kilowatt-hours unit integrated with photovoltaic generation at University of Évora, Portugal. A 100 kilowatts, 1.26 megawatt-hours installation is planned for the island of Gigha, Scotland. A 5 megawatts, 10 MWh system at the Wanyushi wind power farm was connected to the Liaoning power grid, China, on the 23rd of May 2013. 1 megawatt, 5 megawatt-hours installed by Sumitomo Electric Industries in Yokohama. 100 kilowatts, 600 kilowatt-hours unit, installed by Prudent Energy in Abankolovo, Slovakia. The vanadium redox battery is a type of rechargeable flow battery that employs vanadium ions in different oxidation states to store chemical potential energy. The vanadium redox battery exploits the ability of vanadium to exist in solution in 4 different oxidation states, and uses this property to make a battery that has just one electroactive Sumitomo in Japan and H2 Inc. in South Korea. The main advantages of the vanadium redox battery are that it can offer almost unlimited capacity simply by using larger storage tanks. It can be left completely discharged for long periods with no ill effects. It can be recharged simply by replacing the electrolyte if no ampellegri and spazienta. The first successful demonstration of the all-vanadium redox flow battery employing vanadium in a solution of sulfuric acid in each half was by Maria SKYLLAS-KAZACOS and co-workers at the University of New South Wales in the 1980s. Their design used sulfuric acid electrolytes, and was patented by the Universe Element instead of 2. For several reasons, including their relatively bulky size, most vanadium batteries are currently used for grid energy storage, such as being attached to power plants or electrical grids. Building on earlier research on flow batteries, the possibility of creating a vanadium battery was explored variously by PISORT, NASA Research's University of New South Wales in Australia in 1986. Organizations involved in funding and developing vanadium redox batteries include Uni Energy Technologies and Ashlawn Energy in the United States, Renewable Energy Dynamics Technology in Ireland, Gildemeister AG in Germany, Selenium in Thailand, Ronca Power and Prudent Energy in China.